All right, everyone, I think we'll start. Just a bit of housekeeping first of all. So we'll be recording this, and this will be put on our YouTube probably next week because our Marcoms person is away. And you'll also get the materials probably a little later than usual. Just so everyone understands, everyone could turn off their microphone and their cameras, please. That'd be really helpful. That means we can just sort of focus on our speaker for today. And in terms of chats, we'll take chats at the end of the talk, but if you could put them in the chat, I'll read them out, but maybe prompt you if there's any clarifications needed. Okay, so a little introduction first. I'm Stephen Haven. I'm a data science consultant at the Energy Systems Catapult here in the UK. Welcome, everybody, and thanks a lot for joining us for this, what we call a Value in Energy Data seminar, where we look at everything data and digital in energy systems. I'm very pleased to introduce our speaker today, who's going to be Assistant Professor Hussain Kazmi from KU Leuven. I'll give you a little bio and then I'll let him go ahead with the talk. So Hussain is currently focusing on data science and decision support tools for the energy transition. And in the past, he's been a visiting researcher at the Imperial College London, National University of Singapore, and KTH Royal Institute of Technology in Sweden. He has also played key roles in several clean energy startups and was granted the International Institute of Forecasters Annual Award for his work on value-orientated forecasting in 2021. And currently he's working in the context of an EIT InnoEnergy project, where he coordinates a cross-European working group on energy data science. So I'm very pleased to introduce Hussain today, who's going to be talking about the exciting intersection of data and knowledge for energy modeling and control. So thank you very much, and I'll let you take away, Hussain.
All right. Thank you, Stephen, for the very kind introduction. I will try to share my screen. All right, please let me know if you can see my screen.
Yep, I see it. It's now it's in presentation mode. Brilliant. Thank you.
Right, brilliant. Okay, thanks everyone for joining. My name is Hussain Kazmi, as Stephen just introduced me. I'm an assistant professor of energy and data science at KU Leuven, which is a university in Belgium. I will talk about the intersection of data and knowledge, which fits in with the whole theme of the webinar series quite well. And I'll specifically talk about modeling and control of distributed energy resources such as heat pumps, batteries, if you have the time for that. But we will primarily focus on heat pumps today. Before we get started, a bit about KU Leuven. So we are celebrating our 600th year anniversary next year. So that will be in 2025. We are one of the oldest universities in Europe, but certainly in the lowlands, so Belgium and the Netherlands, and also one of the biggest. So with the Department of Electrical Engineering, we have our campus slightly outside of the center of Leuven. So that's the top left castle that you see. We actually work right next to it, so we have a very nice view of the castle. But we also have another campus that many of you may have heard of, that's known as Energieville. It's around 50-60 kilometers away from Leuven in a town called Genk. And that's basically where we work together with other research institutes from Belgium, so VIED and IMEC, and also the University of Hasselt, together on problems related to the energy transition. A bit about the presentation today. So I will briefly cover the need for energy flexibility to begin with. Then I will talk about the different types of modeling strategies that people have used to model flexibility. I will discuss briefly some of the challenges that arise with specifically the data-driven modeling of flexibility. So how do you use data-driven techniques such as neural networks and whatnot to model the available flexibility from residential buildings? I will discuss some potential solutions and opportunities that we have seen emerge in our own research in the past few years. And I will finally conclude with some ongoing activities that my group has on benchmarking predictive models for the energy space. So this is a slide that I like because it shows that we are making progress in the energy transition, but it is also a slide that perhaps rings a few alarm bells for the transmission grid, because what we see here is that on the blue and the green curves, we see quite a rapid increase in the buildup of electricity generation via renewables. So those are the solar and wind installed capacities for the country of Belgium. And the data that you see here is for the last 7 years. So in that time, we have seen more than tripling of installed capacity, and that basically creates a lot of uncertainty on the transmission grid in terms of whether there will be enough power generation available or not. This also means that the whole system becomes a lot more uncertain, which creates the need for extra energy flexibility to make sure that the system continues to operate in a stable manner. You can see this in this plot that we have generated using openly available forecast data from the Belgian transmission grid at 3 different timescales. So you have the week ahead forecasts, you have the day ahead forecasts, and you have the, well, close to hour ahead forecasts as well. And what you can see is that in absolute unnormalized terms, the forecast errors have, well, increased very rapidly over the last 6 to 7 years, and they are not really showing any signs of stopping at all horizons. Now, people say that this is primarily because of the increased installed capacity that we have, and that is certainly true to an extent. But what is more concerning is that we have also seen a deterioration in the skill score of these forecasts, which means, on the one hand, that there is an opportunity to improve the forecasting of these renewable energy sources. But at the same time, it means that there is a need for energy flexibility schemes to step in and make sure that when we make big forecast errors, then they can still be mitigated in time. There are also stresses arising from the demand side. Over the last few decades, electricity demand in most European countries has stayed rather flat. In some cases, it has even gone down a bit, as is the case in Belgium. But this trend is probably going to reverse in the coming decade with increasing electrification of demand, transport, industry, and heat. So this is a figure from Belgium, where we see that the increase in electricity is going to be primarily driven by industrial demand, but also transportation, which includes both the private electric vehicles, but also electric trucks and buses. And then finally, we will also see quite a lot more of electric heating that will replace gas-based or coal-based heating that has existed historically. One thing to keep in mind is that on this plot, you can see that the expected or foreseen electricity demand a decade from now is somewhere around 130 terawatt hours, which is more than 50% of what we have today. But if you look at the generation forecasts for the next decade for Belgium, we do not see them going much above 100 terawatt hours in most scenarios. That leaves a supply-demand gap on an annual basis of around 30 terawatt hours, which is quite a big number for a European context. Now, to contextualize that, quite a few people think that some of this demand can be met by importing electricity either cross-border or through long-distance high-voltage cables. This is, of course, true, but at the same time, it also introduces extra stressors and risks into the operation of the electrical grid, which means that flexibility is going to become more and more important, that we can consume electricity when it is available, and then we don't consume it when it's not available anymore. So those are some of the motivations for energy flexibility from the transmission grid operator's perspective, but there are also increasingly problems on the distribution grid that are becoming even more pressing and urgent. So this is a plot from the capacity card in the Netherlands. We don't yet have the same problem in Belgium or in many other countries, but I assume that these problems will arise here and elsewhere as well. So the Netherlands has one of the highest per capita installations of solar PV in Europe and indeed worldwide as well. And that has arguably contributed a lot to problems with the distribution grid, as you can see here. So basically what you see on this plot is that all the regions that are in red, those are regions where you cannot essentially have a new electricity connection anymore. So you cannot really, well, basically start a new business or many of these things, uh, simply because there is no capacity on the distribution system to connect to it. The regions in dark orange, they are also regions where there are significant problems that hopefully will be resolved. But again, these are things that are problems now. And there are only two solutions to fix this. On the one hand, you can go for expensive grid reinforcements. And on the other hand, we can go for energy flexibility from assets that are distributed in the distribution grid itself. On the transmission side, there are also big opportunities for energy flexibility as foreseen by the transmission system operator. So just in Belgium alone, we estimate that these numbers are going to be in the hundreds of millions of euros on an annual basis in the coming decades. This is basically in terms of avoided generation capacity that needs to be installed, that can then simply be replaced by energy flexibility. But to do this, what we will require is for most of the new electrification of demand to be flexible or be flexible to a certain extent. This means that more than half of the new industrial demand, as well as most of the residential demand, will need to be operated in a flexible manner. And what I mean by a flexible manner simply means that you have demand that responds to either price signals or direct control commands. At the moment, this is certainly not the case because much of the electricity demand that we have on the power system is largely inelastic and inflexible, but this will certainly change or have to change in the coming years. This also means an essential rethink in the way that we organize the electrical power system. So on the one hand, at the moment, we see that we have only a handful of flexible assets in Belgium. This has certainly changed in the last few years since I started giving talks like this. And now we have quite a few flexible assets already that are operating in the different types of markets. But in the coming years, this is going to grow very rapidly into the sense that we will have hundreds of thousands or even millions of flexible assets that will need to be controlled in real time. And that will require a very good understanding of how these systems work on the one hand and how they respond to different types of control commands on the other. So for example, if the prices change, how do the electricity demand from these systems change in real time? So what you see here is that at the moment, most of the flexibility we have in Belgium comes from pumped storage, but also only a tiny bit from large-scale storage that is both in the market and part of it which is out of the market. But over the next decade, these numbers are expected to completely flip in the sense that pumped storage will form a much smaller percentage of the actual available flexibility. And that will be outweighed mostly by both storage technologies as well as vehicle-to-grid technologies. Increasingly, we also see grid operators looking into electric heating and heat pumps as a source of flexibility that will take a very important part in the future grid. So the first question that emerges at this point is, how do we take control of this flexibility? How do we actually even model it? And historically, for obvious reasons, this has been done in a physics-based method, following physics-based methods. So these are models of the systems that have been crafted by human domain experts. So you could think about these as models that explain how the industrial processes work or how the HVAC systems in large industrial or commercial buildings operate. So you can really understand that if you change the set points, how is the heat pump or the HVAC system going to respond to that from an energy perspective, and then you can use that in a closed loop system or perhaps a different type of controller to respond to prices that are communicated by the grid. The obvious advantage of this kind of method is that it is very well understood since human domain experts have crafted it. It is also rather trustworthy in the sense that if there are problems with the system, then a human domain expert can quite quickly and easily debug the system overall. It is still quite complicated and clunky because a human domain expert has to go in and build all of these systems from scratch. At the same time, it is also often the case that these systems are not super adaptive. So if something changes or breaks in the system and there is no feedback loop from the data, then you basically have an outdated model of the system, which is being driven into regions of the state space that don't necessarily make a lot of sense. But the biggest problem with these systems is, of course, that it is just prohibitively expensive to build individual bespoke models for hundreds of thousands or even millions of assets. So this is just completely infeasible, and that's the biggest bottleneck that we have in realizing the energy transition with lots and lots of flexibility on the power system. What a lot of people have gravitated towards in the past few years is, of course, data-driven methods. Just like in every other field, we have seen a proliferation of AI-based models. And the hope is that it is much cheaper to construct these models as opposed to human domain expert-based models, since they only rely on observational data. Of course, there are several problems with this, and I will go into a bit more detail on this in the following slides. But of course, the first problem and the biggest one is the poor quality of data and the simple lack of availability of it. There are also challenges on the algorithmic side, in the sense that if we fit neural networks or other types of black box models to biased and incomplete data, then we cannot really hope to obtain models that follow causal relationships between input and output variables. Diving in a bit deeper, so this was a study that we did together with some colleagues from different universities in Europe. So it's already 4 or 5 years ago that we did this study, so probably things have changed a bit. But when we started looking into the availability of open source smart meter data from countries across the world for both residential and commercial buildings, we saw that it wasn't really that well distributed across the whole planet. So there were big blind spots in the availability of smart meter data. So for example, if you were working in Africa or somewhere in South America, you would have very little visibility on what you could expect using just open source datasets. Of course, if you're a utility, you can go in and you can collect your own datasets, but that, of course, comes with lots and lots of costs. Things get even worse if you start diving a bit more into details. So what I just showed you was just simple smart meter data. But if you start thinking about what you need to unlock energy flexibility, you actually need sub-meter data and perhaps data that reflects different types of interventions, where a signal was communicated to a building and then it responded to that signal in a certain way. These data sets are even rarer. So in a study that was conducted by colleagues from the International Energy Agency Annex 82 or 81, we found that of the more than 300 papers that have been published on energy flexibility, only 4 of them come with open source data sets that are available and open to reuse by the community. And that's a shockingly low number. So that simply means that we don't have any reproducibility of most of the studies that have been published. But that also means that unless if you have a way of obtaining data on your own, in many cases, you will not really be able to do something creative without going in and acquiring data. Availability of data is, of course, the first problem, but even when data is available, the quality is often questionable as well, at best. So this is a large-scale study that we ran on many different open source available data sets that have been collected in the last decade. So you will see some familiar names that people have been using to benchmark their forecasting algorithms and other types of algorithms. And what we see there is that the quality is rather rubbish across the board. So the way to read these plots is that on each of the columns, you have essentially a time step. So this, for example, data set goes from 2009 until 2010. And each of the rows is an individual building that is present in the data. So the Irish CER dataset contains roughly 6,000 buildings. The UK low carbon dataset contains roughly 5,000 buildings. The BDG2 dataset contains close to 1,500 to 2,000 buildings, and the Osgrid dataset also contains hundreds of buildings. But what you see is that there are long horizontal streaks, which essentially mean that particular buildings in this dataset have data missing for protracted periods of time. And you also see vertical streaks, which basically means that at a certain point in time, all the buildings in a data set are essentially missing a lot of data. You also see a lot of both vertical and horizontal streaks combined together, which essentially mean that you have data for many buildings missing for a large period of time. Now, if you have to fit predictive models using data of this quality, this is always going to be quite tricky, and that's something that we have witnessed over and over again in our own work as well. Unfortunately, that's the kind of data that we have available to us, primarily as academics. In some companies, the data quality is sometimes a bit better, but often many practitioners also have to suffer through the same type of data issues. And that means that many of the models that are built using these corrupted or low quality data sets are only tested for accuracy, using simple metrics like mean absolute error, or increasingly nowadays relative mean absolute error metrics. This is typically not good enough, because in practice you also care about how scalable your model is. So for example, how does it scale as you get more and more data? How does it scale as you get more and more features? But at the same time, it also has to be robust in a certain sense that, for example, if some of those features do not make through in time, how does your model respond to that? Does it just completely not produce any predictions? Does it fail but in a graceful manner? Or does it still produce predictions that make sense to the best of its abilities? Another dimension that's also quite important is that we have to move beyond the narrow confines of accuracy and consider what happens to the model when it is not sure about its predictions. So can it produce uncertainty estimates? Can we explain why the model is producing a certain prediction or not? And whether the predictions that the model is producing, are they following known domain principles or not? And this is quite a key concern if we want to have trustworthy systems, because as we discussed earlier, physics-based systems possess this property, but data-driven methods do not necessarily have this out of the box. And we have to enforce certain limitations or constraints on those models to make sure that this happens in reality. So the question then emerges or arises that how do we obtain these models? There are a few different ways that have been explored by researchers and practitioners on making this so. We will look into a couple of case studies in the next slides. But to begin with, what you can do is you can start to incorporate additional sources of information into your black box models. So this could be combining data with different sources of information, such as physics, or data that you have collected for similar buildings or similar instances. What you can also try to do is you can try to clean up the data in a way that makes it a bit better suited to predictive modeling. And this is one of the core conclusions from the Great Energy Predictor 3 competition that concluded a few years ago, that pre-processing basically trumps most predictive algorithms. So that's something to keep in mind. And finally, if you really know what you are trying to do with your system, with the black box model that you're fitting, perhaps you do not need to minimize for the mean squared error, but you can modify that score to do something a bit better. So for example, to mitigate the double penalty effect, or like all these problems that you that you face when you're building these black box models. So I will talk about a large-scale project that we ran a few years ago, and that was quite a nice testbed to explore many of these ideas. So this was a project that was called Renovates, and a few other projects that also lie in the same constellation of ideas. The core idea is that we want to decarbonize the built environment or the housing stock in general across Europe. Now there are a few different ways of doing that. The first set of techniques that we can employ are passive. So this includes what happened in this project, that we took poor efficiency social houses, we replaced the facade by high efficiency, high quality materials that reduce the different type of thermal losses from the buildings. Then in the second step, we replaced the gas-based heating in these buildings, which was rather low efficiency and polluting, with high efficiency air source heat pumps. And then finally, to meet the residual electricity demand in these buildings, we replaced, we did not replace anything. We also added solar PV systems on the rooftops. So those were 6 to 8 kilowatt peak solar panels installed on each rooftop in houses across the neighborhood, as you can see here. This basically meant that these houses were intended to be net zero energy or net zero energy on the grid, but they actually turned out to be positive energy. So this plot shows you on the x-axis what is the annual electricity demand from these buildings, and on the y-axis you see what's the actual generation from the individual houses in this neighborhood. The two different colors of the dots represent the years. So we were looking at this from 2019 to 2020, and you also see each of the individual dots is an individual household or building. And then you can see that instead of being net zero energy buildings, these are positive energy buildings because most of them lie above the actual line where you would expect a net zero energy building to lie. So these are essentially generating more electricity than they are consuming over the course of a year. Now, this is a great outcome from a sustainability perspective, that we can basically transform houses from being electricity consumers to electricity net exporters. But it's very bad news for the electrical grid, because this is how you get to the sea of red on the distribution system, because now you have solar panels that are pumping electricity into the grid during the summer in a very correlated manner. And then during the winter, all the houses are basically taking electricity from the grid to meet the electrical heating load. So that is indeed what we saw in this project as well. But first, I will show you how the actual sub-metered loads look like. So here you see that we have the demand, and that is more or less evenly split between the appliances in these buildings and the heat pumps in the buildings. So they are roughly on the same order of magnitude for almost all the houses. And then the heat pump load can be further split almost equally between the electrical heating loads and the hot water production loads. So this was roughly on the same order of magnitude. We didn't really see too many differences here. Okay, so the only flexible loads that we had in these buildings were the heat pumps. Of course, you could also consider the solar panel as a flexible generator, because you can always curtail it. But if you talk about curtailing renewable electricity, that is often creating a visceral response in people. So we decided to focus primarily on the heat pumps and the space heating and the hot water circuits more concretely. So we began with looking at the space heating circuit, but before we do that, I want to introduce the different types of data that we were recording in these buildings. So what we were recording was the ambient temperatures naturally, but we were also recording the state of the storage vessel through a temperature sensor. We were also recording the temperature in the living room, the requested set point in the living room, the flow of hot water from the storage vessel, as well as the overall electricity demand from the buildings. You can see in this plot what happened in these households in terms of consuming electricity as a function of ambient temperature. So what we see here is that as the ambient temperature increases, the heating load goes down quite rapidly, to the point that beyond 18 degrees Celsius, we do not essentially have any electricity demand for heating. And that's essentially something that means that in the summer period, we do not have any electricity demand from the heat pump to begin with. And that means that there is no flexibility that's available either to go along with the electricity demand. We also saw that there was quite a big correlation between the set points that the people had in these buildings to the electricity demand for heating. Again, this doesn't really matter too much because there is no flexibility during the summer months, but during the winter months, this does mean that we could play with the set points a bit to increase or decrease the amount of energy that the heat pump consumes at a given point in time to help the operation of the grid a bit. So this brings me to the crux of the presentation, where we look into the flexibility that is offered by the hot water storage tanks available in all of these households. These are around 200-liter storage vessels that are identical, and they are installed in all the 40-ish households that are present in the neighborhood. For each of these storage vessels, we measure the midpoint temperature sensor. So we measure the midpoint temperature with a sensor. We also measure how much hot water is flowing out of the storage vessel. In some of the buildings, for validation purposes, we also measure the temperature here and the temperature of the water that flows into the storage vessel. We also measure how much electricity the heat pump consumes to heat up the storage vessel, given a certain specific initial condition. And we also measure the ambient temperature, as I mentioned earlier. Now, these storage vessels, they are not perfectly mixed. There is a degree of stratification, so hot water does rise to the top, which means that there is a temperature gradient that looks something like this. The only thing is that we absolutely have no way of knowing how this distribution looks like in general, because we do not observe the entire distribution. We only observe the distribution sampled at this particular point. At the same time, we also do not really have any view on how much heat or how much electricity the heat pump is going to take to reheat the storage vessel from a given state of charge to 100% again. These are both critical pieces of information if we want to use the flexibility of these systems to provide stability to the distribution system, or to shift the electricity demand from these heat pumps to times when there is more availability from the solar panels on the rooftop. So this means that we want to build different types of models that are data-driven, because we have already ruled out physics-based systems. But for those data-driven methods, we still want them to be control-oriented. And what that means is we want them to respect physics of the system, and also respect the different types of input and output relationships that we know to exist based on domain principles. So to pose it more formally, what we say is that given that we have observational time series for water temperature, for hot water usage, for ambient temperatures and heating set points, we want to learn treatment effect models that can predict basically the state of charge in the vessel as a function of when it was reheated. And we also want to predict the heat pump response to reheating the storage vessel from any given state of charge of the vessel. So those are the two key learning tasks that we want to look into. And once we have these, then we can use this information or use these models to operate the storage vessel and the heat pump in a more flexible manner. So there are a few different ways of doing this, and we start with the simplest. So we just start with a purely data-driven learning approach, where we fit a neural network to all the input data that we have. We extract some features from it, and then what we do is we try to learn how much electrical energy the heat pump is going to take to reheat the storage vessel from any given state of charge back to 100%. When we do this, we obtain these kind of plots. So for 1 week of training data, when we evaluate it on an unseen evaluation set, then we see that the R-squared score is quite limited, but at the same time, the observations and predictions do not necessarily line up with each other, even though there is some, let's say, correlation between the two. When we observe this particular system for 8 months or around 32 weeks, then we see that the quality of the model that we learn is much better. So there is an R-squared at this point that is approaching 0.8. So that's almost good enough for control applications. And then you can also see that observations and predictions line up rather nicely for the most part, unless if you're talking about very high energy demand periods, and those specifically refer to extreme conditions during the winter period that are not necessarily very well observed in the training period. This is okay, but we also don't want to wait for a year or even more to learn a data-driven model before we can start controlling a system. So it's quite obvious at this point that we want something which is a bit more data efficient or sample efficient, as we call it. So we try a different approach, a second approach, which basically goes into the direction of collaborative learning, which is essentially that we say that in this particular neighborhood, we have many different heat pumps that have been installed that are essentially identical. Why don't we combine or aggregate the data from all of them and learn a unified representation for the heat pump systems? If we do this by combining data from 32 different households for a single week, we already get an accuracy score, which is very close to learning the model with one household for 32 weeks of data. So if you just look at the R-squared score, you would be tempted to think that these are quite comparable because this is 0.7 and that was 0.77, so rather close to each other. But you can also see based on the scatter plot that this has not learned the same quality of representation as the previous model. So we really need to see a bit more in detail on what these systems have learned. And in this case, it's quite obvious that this one hasn't learned a causal relationship, essentially. However, if we also collect 8 months of data for these 32 buildings, so the same amount of data that we had previously, then we see a model that has learned to predict very well for the entire state space. So no matter where we sample from the evaluation test set, we essentially get a very good accuracy score. And we also get very good guarantees on the causal relationships between the input variables and the output variables. Now, at this point, we can pause and question, why does this actually even work? And the answer to that is essentially this works because we have a lot of different types of buildings that are generating very different types of data sets. And that means that the exploration of the state space is much better if we combine data from many different types of buildings. This leads to models that are richer and that can generalize better. So that's, I would say, the shorthand way of saying, why does this work in the first place? I will skip this in the interest of time, but the question also arises at this point that does this work with similar systems, but the systems being non-identical? So far we have looked at identical systems, but we have also looked into similar systems. So heat pumps that were different, but still rather similar because they were operating in very similar contexts, but they were just built by different companies. And when we do that, then we see that in a transfer learning context, this is also something that works very well and very quickly, that we pre-train the model on large amounts of available data. Then we get a new type of heat pump or a new particular building or a new system. We simply fine-tune that with different types of transfer learning techniques like feature induction or parameter induction, and we see that we get very good results with less than a few weeks of data availability as well. So again, this is, I would say, kind of a nice proof that this system is working. in a bit broader settings than purely identical systems. There are some limitations, of course. So it doesn't work when the agents that we are observing are not different enough. So this means that, for example, if they're all observing very similar data sets, then this does not really bring a lot of value because they all generate very similar data. And then it doesn't really matter if you see that particular data point once or 10 times. But there is also a second caveat to this as well, that when we look at these cyber-physical systems, they usually do not generate data for catastrophic failure situations. So we don't necessarily see data for extreme conditions too often, which means that you will never have a black box model that will be able to learn the boundary between normal operating conditions and extreme operating conditions. So it just fails to generalize in that sense. A second case in which this fails, quite curiously, is exactly the opposite, when the different agents are generating data that is too different. This does not work in collaborative settings, but this is something that we have seen happening a lot in federated learning settings, which we don't have, unfortunately, enough time to go into. But this is something that happens in distributed settings, that if you, instead of sharing the data, you share the gradients or the model updates from the data that you've learned, then this stops to work. So if you have model updates that are being generated after being trained on data sets which are very different, then this is not going to work in general. So is there a different type of technique that we can add here that can improve the modeling performance even further? And the answer to that is also yes, that we can basically generate synthetic data that's guided by domain principles, and that allows us to further improve the performance of these models, not necessarily in terms of accuracy, but certainly in terms of the causal relationships that they learn between the input variables that we provide and the output variables that they have to predict. So in this case, this is the graph where the regular workflow would be that we would not have any domain augmentation, and then you would simply take your engineered features, you would learn them, you would put them through a model, and you would evaluate them. But if you have augmented features, then basically you would combine that with your data set, and then you would learn a model, and then you would evaluate it, and that would really improve the performance of your model quite substantially. How do we do this data augmentation? So there are many different ways of doing it. We have some people who are looking into GANs, some people who are looking into diffusion models, some people who are looking into purely constructivist methods. But in many cases, when you're working with thermal systems or with physical systems, you actually have access to a lot of domain information that you can use to generate additional data. And this could be, sorry, I hear someone. Could you please mute yourself? Okay. Not sure what's happening, but okay, I will proceed anyway. Okay, so you can generate this data based on a few known rules, and these can be thermodynamic principles-based rules, for example, that, for example, you can talk about stratification levels in the storage vessel. You can say that as time goes on, water temperatures have to go down. So that's just thermodynamic losses that take place in any case. You can also have mixing losses that occur. So for example, if users consume hot water from the storage vessel, then the temperature has to go down. You also have stratification, and for example, the idea that hot water generally rises to the top of the storage vessel, so you will have a gradient in that direction. So you can always encode these types of data into your augmented data set, and then you can combine this with the learning process to provide the learning model some kind of extreme indications about what happens in extreme cases. Again, if you already know the PDE or the partial differential equation that governs the system, then you can also just complete the loop and learn a physics-informed neural network rather than perform these kind of, let's say, hacks to learn something which is physics constrained. But that really places a lot more requirements on the ability to model the system as a differential equation that accurately reflects the entire system. So how does this work in practice? Quite well. So if you don't have any data augmentation, that's this extreme left, we see that the actual error performance is quite poor. On the average, we see a mean absolute error, which is around 2-3 degrees Celsius. That drops to around half a degree if we perform some data augmentation using domain principles. So this is really like a case where we can improve both the accuracy as well as the causality of these models by combining the data together with the physics information in a very simple and easy to understand framework. There are a lot more possibilities and there is a lot more potential to explore here, but we don't have time for that in this presentation to go into. So I will move now to the control part and then quickly wrap up. So what you see here is applying these models to an actual neighborhood where we were controlling buildings for an entire year. And what we saw there was that if we use the models that we have just showed you, then we could get a roughly 20% increase in the amount of energy that was being consumed to heat up the storage vessels in the buildings. We also saw that you could use the same models to improve the solar self-consumption and provide flexibility to the electrical grid. And that's the subject of another paper that will hopefully come up in the coming weeks. We also saw that you could use the same principles for more general control. So it doesn't really matter if you're trying to model heat pumps or if you're trying to model electric batteries or electric vehicles. You could even consider direct controllers. So this is a paper that we did on physics-informed reinforcement learning, where what we did was we tried to show that if you had a few batteries distributed in a distribution network, could you control them in a way without knowing too much about the network state, without knowing too much about the load profiles in the system even? Could you control these batteries in a way that could reduce the overvoltages and the undervoltages and all kinds of congestion events in the grid? And then what we saw was that if you pre-train the neural networks that are going to control these batteries for tens of years on all kinds of different profiles, they're already able to learn the optimal policy that you can then apply and basically reduce drastically the number of over and under voltages in the system. To wrap up, this is a figure that has made the rounds quite a lot in the past few years. And this basically says that when we have a lot of data, then we don't necessarily need knowledge about physics. But when we have very few data points, then it is useful to bring in a lot of physics to the problem. Now, how do we bring this physics to the problem? That can be via PDEs, that can be via data augmentation, that can be via loss function augmentation, that can be done through a bunch of different things. But one thing that this figure is missing, in my opinion, is that it makes the distinction between big data and small data. But it doesn't necessarily say anything about the quality or the biasness of that data. And that's also a very important concern, as we see in energy systems, that you can collect a lot of data, but often it is very biased data and it doesn't really let you learn good representations of reality. To wrap up, I hope I still have 1 or 2 more minutes, Stephen, but this is really wrapping up.
Yeah, sure.
Okay, great. So these are just like 2 activities that my research group in Leuven is setting up now. The first one is something that we call InfoBench. So this is motivated by the fact that there have been 50 million different papers that have been published in just the last year that people have shown that they have build a new LSTM, a new transformer, a new some other type of model that works the best in predicting electricity demand, electricity generation, electricity prices, or whatever. 0.1% or 1% or 10% better than everything else that's on the market, but there is no real common benchmark, at least as far as we are aware. And what we are trying to do here, together with a lot of colleagues from the International Energy Agency, Annex 81 and 82, is that we are trying to build a common benchmark, a common framework which contains a lot of different types of electricity load profiles, electricity generation profiles, and then people can basically bring in their their forecast models, they can test them, and then we will see where they end up on this line. If they go above an RMAE value of 1, that essentially means that they are not doing better than a simple persistence baseline, in which case you will see some pretty famous models here. But that's also the thing that we want to just bring this visibility to the community. So if you're interested, we are always looking for volunteers who are interested in contributing with their models. Feel free to use this QR code or reach out to me after the talk and we can discuss this in more detail. The other thing that we are trying to also bring a bit more visibility on is via an open dashboard on electricity prices. So these are price forecasts that we are making now every day for Belgium, that we hope to then make available to the entire community. So you can already go and take a look. We also provide conformal predictions and uncertainty estimates on the price predictions. So you can see for the last 10 days, this has been quite a decent prediction. There is no guarantee, of course, because this is a completely free service. But what we hope to do with this is, again, that we hope to bring more visibility on the quality of these methods and also how people are using them. So with that, I thank you very much for your attention. And if there are any questions, I will be around to answer them.
Brilliant. Thank you very much. That was excellent. Really interesting talk. There's quite a lot of questions, actually, so we'll just get through to them, really. Maxim asked first one about, have you experienced working with large time series models that are trained in self-supervised manner and offer opportunities for zero-shot predictions? How does this performance compare with classical models trained on domain-specific data?
Yep, so two types of models, I guess, to answer that question. The first one is really like models of the type of treatment or cause and treatment effects that are really trying to learn the treatment variables effects from a lot of data. These are things that can generally benefit a lot from pre-training because they kind of understand or start to understand the domain a lot better than if you just show it 2 weeks of data and then hope to learn something from that. On a forecasting side, there we haven't really had a lot of experience yet. For some things, we have seen very good results. So we have a paper under review in the IJF that's specifically on solar forecasting, where we pre-trained the model using tons of simulated data. And then we basically transfer it to new sites. And there we see enormous performance updates. Performance upgrades. But more generally with these type of models like Amazon's Chronos or like all the different time GPTs and stuff like that, there the evidence so far has been a bit more mixed. So we have seen sometimes that they perform quite okay. Other times we have seen that zero-shot performance is quite poor. That is actually even poorer than simple persistence models. So it would actually be much better off just taking the naive persistence model. So it really depends case to case. I would say that for physical systems, these kind of things can work a lot better. For very variable, noisy time series like electricity load profiles, it's a bit of a hit and miss.
Great, thank you very much. There's two questions from Ben really tied together, actually. One is about how scalable is a unified learning approach? Would that require to have loads of identically built houses? But kind of really the point seems to be getting at here is in the second part, which is about, is the housing stock in Belgium homogeneous enough for the pre-training on large data sets to work well?
Yeah, that's a great question. And actually, if you will see the slides, I actually used the example from the Netherlands. And that's not because I did my work in the Netherlands, but that was simply because the housing stock in the Netherlands is quite unique in a European context because there is millions of social houses, unlike most other European countries, and these social houses are being refurbished in a rather uniform manner. So many of them are undergoing the same refurbishments, which means that they are quite, not if not identical, very similar to each other. The housing stock in Belgium is a lot less uniform and a lot less homogeneous. And there, what we have seen is that techniques like transfer learning work better than collaborative learning, that you pre-train on something and then you fine-tune using the actual site's data. So zero-shot learning works a bit worse in this context.
Quite interesting, exactly with the slide you showed as well, with the bias in the data, actually. Have you looked at anything like that, or have you come across stuff which looks at sort of a cross-country type transfer learning? Seems to be
Not
very
yet.
biased, actually, as well.
Yeah, indeed. Not
Good,
yet,
thank you.
but that's interesting.
Yes, links in with what I think you were saying earlier. Wakar asks, can you please specify which types of neural networks are used for time series modeling? I guess maybe the ones that you've been using. Maybe you can say a little bit more about them.
Yeah, so we don't necessarily have a preference. So the neural networks that I showed to model the cause and effect relationships, those were simple MLPs. So not even deep neural networks, although we call them deep neural networks, but they were like 2 or 3 hidden layers, nothing fancy at all. In some other cases for time series forecasting, we have had okay experiences with LSTMs and transformers, but nothing spectacular, to be honest. So at this point, like, the architecture itself feels a bit secondary. But you can also think about it as a way to inject different types of biases into your learning problem. So, like, for me, at this point, it seems that injecting biases based on the loss function or based on the training data seems to be more effective than the learning function itself. That most of the learning functions seem to be doing okay. And we haven't really seen like huge differences in performance across them.
Thank you very much. We've got a question from David Hawkins, which asks, can you give an example of how this data analysis works in practice to assist energy companies in controlling their asset demand generation? I guess also whether you've actually talked to energy companies about doing some of this stuff.
Yep. Yeah, so that was one of the final slides, and we didn't have enough time to go into the control aspects. But indeed, the whole idea of learning these cause-effect models or these treatment variable effect models is that if you build a data-driven model, then you should have the flexibility and capability to use it in a controller. If you simply train a neural network with no guarantees on causality or any of that sense, then essentially you don't tell the neural network that it has to focus on learning the effect of the treatment variable. So for example, it can completely discount or discard the effect of heating the building or the heating power that you're giving to the building, and then it will learn the completely wrong association, for example, because you're providing it biased data that during the winter, the heating is always on, which essentially means that the temperature is always stable. So the model might learn the incorrect association that it's actually colder temperatures outside that cause the temperature indoors to be very stable. And if you learn a model like this, and then you start using that in downstream services, for example, to provide FCR or like different types of frequency regulation or different types of arbitrage or responding to price signals from the DNO or the TSO, you're basically not going to be able to get very far with these models. So it's really like a function of what you want to do downstream that kind of constrains the types of models that you're learning upstream. And if you do not have these kind of causal models, then for flexibility services, I do not think that you should be using data-driven models.
Brilliant, thank you. I unfortunately think we run out of time, but there's plenty more questions down there. Feel free to get in contact with Hussain. He's happy to email if there's any important questions. A big thank you again to Hussain Kazmi for the talk today. well, as I say, we'll share probably next week the slides and also the recording, which will be on the playlist, which I put in the chat. But yeah, thank you very much, and I guess we'll see you next time. Take care.
Yep. Thank you for having me, Stephen, and thanks for organizing. Thanks everyone for the nice questions.
Take care.
Thank you. Bye.